And welcome to our 33rd lecture for MAT353. In this portion of today's lecture, we are going to be talking about the two major implications of the fundamental theorem of line integrals. And these are path independence and a result for line integrals along closed curves. I should say here, I suppose, line integrals of conservative vector fields along closed curves. That's somewhat implied, as the fundamental theorem of line integrals only applies to conservative vector fields, so clearly those have to be the vector fields that we're discussing as we're talking about the implications of this important theorem. So we will take these in turn. We will start with the idea of path independence. So what do I mean by path independence? We say that path independence holds for a vector field f hat if you can take any 2 points in the plane, A and B, and you can form any two smooth curves, C1 and C2, that both begin at A and end at B. So it doesn't matter what paths these curves actually follow, just that they begin and end at the same points. If you have that, then for a conservative, if we say that path independence holds for f hat, it will be the case that the line integral of f hat along C1 will be the same as the line integral of f hat along C2. So looking at this picture here, I've got curve C1, which takes a relatively straightforward path from A to B, and I've got curve C2, which does weird stuff as it goes from A to B. It doubles back on itself, it has lots of detours, and it generally takes a much more erratic path from A to B. But they are both smooth curves, there are no corners in them, and they both begin at A and they both end at B. And so what the theorem says that if you have path independence for some vector field f, then the integral of f along C1 will be the same as the integral of f along C2. The path taken doesn't matter, just the two endpoints. So if you think about driving from here to one of my favorite cities, Berkeley, California, it doesn't matter which path you take. You could follow I-70 and go through Wyoming. You could drive down south and hit I-10 and go west on I-10 before going back up north on I-5 once you get to California. It doesn't matter which path you take if all that you're interested in is the total elevation change along that path. So if I leave from here where I'm sitting right now in New Paltz, and maybe I drive up into northern Canada and across the land where there is no roads and then back down to Berkeley, or maybe I go all the way down to Chiapas, Mexico in the southern part of Mexico, or even further down to Panama in the southern part of the North American continent, and then back up to Berkeley, California. The total change in elevation is just going to depend on where I started and where I ended up. It does not depend on the path followed. And that's sort of the intuition behind the idea of path independence. It doesn't matter what path you take, only where you end up and where you began. So as another example here, thinking about changes in energy, if I am going to try to move a heavy stack of books from the first floor of a building to the 5th floor of the building, I could go directly from the 1st floor to the 5th floor, and there would be a change in potential energy associated with those books, gravitational potential. Or I could go from the 1st floor all the way up to the 20th floor, and then from the 20th floor back down to the 5th. The total change in potential energy is going to be the same. It only depends on where I began and where I end up. So let's think about how this relates to conservative vector fields, this idea of path independence. Let's let f hat be a conservative vector field. That means there does exist some little f such that the gradient of little f is given by big F hat. That's what it means to be a conservative vector field. It is the gradient field of some potential function. Is path independence going to hold for this vector field? So let C1 be a curve parameterized by R1, where t, my parameter, is going from A to B and it's smooth. And I'll let C2 be a different curve given by a different parameterization with different bounds on my parameter, here taken to be alpha and beta. And it is also a smooth curve. So C1 and C2 are both smooth curves. They have parameterizations R1 and R2 respectively. And let's also assume that C1 begins at A and C2 also begins at A. So C1 and C2 both begin at the same point in the plane, capital A, and they both end at the same point in the plane, capital B. Then the line integral of vector field f along curve C1 is going to be given by the fundamental theorem of line integrals by the value of my potential function at the end point of this curve minus the value of my potential function at the initial point of this curve, R1 hat of B and R2 hat of B. But those points are just B and A in the plane respectively, so I'm looking at little f at B minus little f at capital A. Capital B is R2 hat of beta, so it was the endpoint of curve C2 as well, and capital A is the initial point of curve C2 as well, so I can replace B and A with these expressions for R2 hat. And then, using the fundamental theorem of line integrals but going backwards in some sense, from the difference of the potential function to the integral of f hat along C2, I have the final line here in this chain of inequalities. And if we follow all the way through here, we're seeing that the integral of f hat along C1 is the same as the integral of f hat along C2. And I am again using the fundamental theorem of line integrals twice in this argument. So yes, it looks like path independence holds for conservative vector fields. It follows from the fact that the line integral of a conservative vector field along a smooth curve only depends on the value of the potential function at the endpoints. You don't actually have to care what happens internal to the curve, just the difference, all that you care about, or the whole story is told by the value of the potential function at the endpoints. So as long as two curves have the same endpoints, we're going to see the same line integrals along those two curves for a conservative vector field, for a single conservative vector field. So we have shown in this little argument that if you have a conservative vector field, path independence holds for that vector field. In fact, more is true. It is also true that if path independence holds for a vector field, you can then conclude that that vector field must be conservative. So I could write this line here above with the implication going the other way as well. That's a trickier argument. It's not one that we're even going to sketch here, but it is true, and we will state it in this theorem. So path independence and conservative vector fields, if f is a conservative, f is a conservative vector field if and only if path independence holds for f. So if you have a vector field that you know to be conservative, you can conclude that path independence holds. If you have a vector field and you can show that path independence holds for that vector field, you can conclude that the vector field is conservative. That other implication, the one that we are not demonstrating, is not really as useful. It's not hard to show that a vector field is conservative, and it is hard to show that path independence holds independently. So trying to show that path independence holds for a vector field from first principles is tricky. So really it's just, we're stating it this way for the sake of completion, and it's always nice to know that two ideas are exactly equivalent, but it's not of as much practical use to go from path independence to concluding that the vector field is conservative. We already have an easy way to check if vector fields are conservative or not. So, that being said, it is quite interesting here theoretically that it is exactly the conservative vector fields for which path independence holds. These are basically the same concept stated in different ways. A vector field being conservative, that is exactly equivalent to the idea of path independence holding for that vector field. Path independence works for conservative vector fields, and they are the only vector fields for which path independence works. Alright, the next major implication of the fundamental theorem of line integrals is going to be how the line integrals of conservative vector fields relate to closed curves. So what are closed curves? Closed curves are curves that end where they begin. So when you close the loop. A formal definition says that if a curve C is given by parameterization r hat of t, where t is between a and b, we call that a closed curve if r hat of a equals r hat of b. And I've sketched a few here. One of them looks like a lemnis gate, the infinity symbol. So it's allowed to cross over itself, and then as long as it comes back and ends where it began, it is a closed curve. And as another example, you might have a circle centered at the origin. That's one that we talk about often, and it is also a closed curve. It ends and begins in the same place. We've put the ending and the beginning point as an emphasized dot along the curve here. Next week, when we begin talking about Green's theorem, we are going to be interested in closed curves that do not self-intersect in the way that this left-hand example does. So we'll talk about simple closed curves, which are closed curves where the only self-intersection occurs at the endpoint. So C2 here is a simple closed curve, but C is closed but not simple. And we'll talk more about that next time. It's not necessary for our current discussion. So those are closed curves. Let us suppose that we have such a closed curve here, C, given by parameterization R hat. And I tell you that it's a closed curve by telling you that R hat of little a is equal to R hat of little b, and those two output vectors for R hat are the point in space A. Let's further assume that we have a conservative vector field F hat, and that a potential function for big F hat is given by little f. Then the integral of big F hat along C by the fundamental theorem of line integrals again. The fundamental theorem of line integrals allows me to write the line integral of this conservative vector field as the difference between the potential function at the two endpoints, but here the two endpoints are the same. It's just a for both of the endpoints, so we get the potential function's value at a minus the potential function's value at a, and whatever that happens to be, I get 0. So if you're dealing with a conservative vector field, then the line integral of that conservative vector field along any closed curve is going to be 0. The fundamental theorem of line integrals tells you that the line integral of a conservative vector field along a curve is just given by the difference between the values of the potential function at the endpoints of the curve, but when those endpoints are the same, that difference will always be 0. And in fact, so we have shown, again, one of the implications. We've showed that if it's conservative, then you always get 0 when you integrate along closed curves. It also is true that if you have a vector field for which you always get 0 as you integrate along closed curves, you can then conclude that that vector field must be conservative. So just as in the first part of today's discussion, or the current discussion, we saw that if the vector field is conservative, then you have path independence, and we also claimed that path independence is enough to conclude conservative. The same is true here. We showed that if we have a conservative vector field, then the integral along closed curves will always be 0, and it's also true that if the integral along closed curves is always 0, that the vector field must be conservative. Again, that reverse implication is not going to be of as much practical use to us, but it is of great theoretical interest. To state the theorem here formally, if you have a continuous vector field f hat, so we do need to go ahead and state that it's continuous, then it's going to be conservative if and only if the integral along all closed curves is 0. All closed smooth curves is going to be 0. So to use my change in elevation analogy from earlier, if we're thinking about what this means, if I start here from my home and I go out and I get my vehicle and I start driving around, it doesn't matter what path I take, how long it is, where it goes, nothing about the path at all matters. As long as I come back and I park my van back in the same spot where it left from, I have seen 0 change in elevation. So there is no total change, regardless if I drive along a bunch of flat highways and come back, or if I drive up through the mountains going up and down constantly. As long as I eventually return back to my home, I have seen no total change in elevation. And this theorem is going to make certain integrals very, very easy. So let's think about an integral given here. Let's think about an example. Here is a vector field f hat, and it's a fairly involved one. So we've got trig functions and exponentials multiplied together, and we've got some functions embedded in each other. And we're also given a curve C here, and it's also somewhat elaborate. We've got multiple trig functions multiplied together, and we've got an exponential of a trig function. I grew a little bit suspicious here when I noticed that the parameters on the bounds rather, on my parameter t are 0 to 2 pi. I know that that's a full cycle for trig functions, and there's lots of trig functions involved in R hat. So I might already begin to suspect that this could be a closed curve C. We are asked to find the contour integral of f hat along C. So this looks like it's going to be involved. If I start trying to find f of r hat and dot that to r hat prime, things are going to get pretty messy. I would like to have a better way. I might begin in the obvious way and try to proceed via the definition of the line integral of that vector field, and things would get quite complicated quite quickly. So I can look forward a bit in my mind and see that that's not going to work well, and I start to think about whether or not there's a better way. I know that things are generally nicer and easier to compute if I'm dealing with conservative vector fields, so my first impulse should be to decide whether or not this is a conservative vector field. To decide that, I'm going to take the partial of the second component function with respect to the first variable x, and I find an expression for that. And I will also check the partial of the first component function with respect to the second variable y. And I can see that those are equal. So they're both somewhat elaborate expressions, but they turn out to be exactly the same, so I am dealing with a conservative vector field. Now I could find a potential function for this conservative vector field, and then evaluate the value of the potential function at the endpoint minus the value of the potential function at the initial point. But things are going to be easier still if the curve turns out to be closed. Then I won't even have to find a potential function. So is this a closed curve? As I mentioned, I saw some trig functions involved in the parameterization of this curve, and I noticed that the bounds on my parameter were 0 and 2 pi. So it seems like there's a fair chance this is a closed curve. So let's have a look at r hat at 0, the initial point, or the lower bound for my parameter t, 0. R hat at 0 is going to turn out to be 0, comma e, and r hat at pi is likewise going to turn out to be 0, comma e. So this curve does begin and end at the exact same point, 0, e, and it is a closed curve. And now I am done. I don't have to find a potential function. I don't have to try to evaluate the potential function at the endpoints of the curve C, because I know I am dealing with a conservative vector field, and the line integral of that conservative vector field along a closed curve C, I can conclude that that integral is 0. Whatever the potential function turns out to be, I'm going to have it at 0e minus it at 0e, and that difference is going to be 0. So I'm done. And again, as I said in the last part of last lecture, if you have been paying attention in this course, you will have learned that I love questions like this, where I can throw a problem at you. The straightforward way of doing it is difficult, if not impossible. In this case, it's wonderful because there are 3 ways to do the problem. You could attempt it from the definition of the line integral, and that's going to be madness. You could also realize that it's a conservative vector field, and so find the potential function and evaluate the potential function at the 2 endpoints. That would be doable, but it would take lots of time. Or you could go a step further, realize that it's a conservative vector field in a closed curve, and immediately conclude that the line integral must be 0. So 3 paths, one that would be insurmountable, one that would be difficult and time-consuming but doable, and one for the most theoretically well-equipped of the students that will be simple, straightforward, and quick. So, a lovely problem in that regard. Let's have you do a sample problem of this type. We're going to do some more practice of fundamental theorem of line integral type problems in the second part of today's lecture, but let's have at least one sample problem here in the first part. So here's a little f, a scalar valued little f, and I'm asking you to find the line integral of the gradient of little f along the unit circle centered at the origin but taken in the clockwise direction. So taken in the opposite direction that we usually consider the unit circle in. So give that some thought, pause the video, we'll discuss it momentarily. Alright, so this is a conservative vector field just because it is a gradient vector field. I already know it's a conservative vector field. In fact, I have the potential function in hand. I would rather not find the gradient of that potential function. The potential function was somewhat involved, and if I can get away without even calculating the gradient, then that's a win for me. So I know that I'm dealing with a conservative vector field because it's explicitly given as a gradient, and I know my curve C is closed. I don't actually know how to parameterize C. I know how to parameterize this circle taking counterclockwise. Parameterizing it clockwise is a bit different. So, I mean, I know how, me, Dr. Felder, knows how, but we haven't discussed it in this class, and you may have gotten it, it's not too terribly difficult. But I don't actually need it. I don't actually need a parameterization, I just need to recognize that it's a closed curve, and that I'm integrating a conservative vector field along that closed curve, and I can conclude straight away that the line integral must be 0. All right, I thank you. We will reconvene for part 2 of today's lecture, where we'll do some practice problems involving the various different applications of the fundamental theorem of line integral that we've been discussing. Thank you, folks.